let's jump right into building a practical, rock-solid network diagnostic toolkit. Today, we're demystifying exactly how your computer talks to itself and, ultimately, how it connects to the outside world. Whether you're a developer, an IT pro, or just someone who really wants to look under the hood of your machine, mastering these built-in checks is an absolute must.
So, how secure is your local server? You might be thinking, hey, my local dev environment is totally locked down on my laptop, I'm good. But asking this question is step one. Because, as you're going to see, a simple misconfiguration can accidentally expose you to your whole local network, or even worse, the public internet. Let's make sure that doesn't happen.
Here's the game plan for our toolkit. We'll start with the mirror test, then do an open window audit, followed by verifying NAT and IPs, and finally we'll wrap up with securing your digital perimeter.
First up, Section 1, Network Health Diagnostic Toolkit, your networking masterclass.
Moving right along to Section 2, the mirror test, basically talking to yourself. To run this mirror test, we use what's called a loopback address. Think of your network like a house. The loopback address, specifically that 127 range, is like your internal intercom system. It absolutely never broadcasts to the street. Any data you send here gets processed entirely internally by your machine's TCP/IP stack.
Put simply, 12.7.0.0.1 just means here. It never even touches your physical network card to go out into the world. It's this beautiful, completely safe sandbox, which makes it perfect for local development and testing out software without needing any internet connection at all. And here is the mirror test in action. By just opening up your command prompt and typing ping 127.0.0.1 for IPv4 or ping : 1 for IPv6, you can instantly verify your network stack. If you get a reply with 0% packet loss, your local TCP/IP stack is totally healthy. If it fails, well, you know for sure the problem is inside your machine, not with your router or your internet provider.
Section 3, the open window audit. Who is actually listening?
Next time you spin up a server, you've got to check how exposed you really are. Look at this massive contrast. Binding to 127.0.0.1 is incredibly secure because it restricts access entirely to local apps on that exact same machine. But binding to 0.0.0.0, which you might know as INA_DDR_any, well, that tells your program to listen for connections on literally every single available network interface.
So, if 127.0.0.1 means here, 0.0.0.0 means anywhere. Back to our house metaphor, configuring a server to listen on 0.0.0.0 is like unlocking every single exterior door and throwing open all the windows. If you're on public Wi-Fi at a coffee shop and your local server is bound to 0.0.0.0, anyone else sipping a latte on that network could potentially get into your server. No good.
To run this audit yourself and see what's hanging wide open, the netstat command is your absolute best friend. Just open your terminal and type netstat-tulnp. This immediately reveals exactly which services are actively listening. Pay close attention to that local address column. Are your dev tools safely bound to 127.0.0.1, or are they sitting out there on 0.0.0.0? Doing this gives you total control over what your machine broadcasts.
Moving to Section 4, verifying NAT and IPs, navigating the neighborhood.
Now we're stepping outside the house to see how it connects to the public street. Ever noticed your home Wi-Fi IP almost always starts with 192.168 or maybe 10. something? That's entirely by design. To keep us from running out of globally unique IPv4 addresses, a standard called RFC 1918 set up these specific address ranges to act like internal room numbers. They are non-routable on the global internet, strictly for private networks.
But wait, if your laptop has a private IP that can't be routed online, how are you even watching this explainer right now? Enter NAT, or Network Address Translation. NAT is the bridge. It translates your local private IPs into the one single global public IP assigned by your provider. So external websites never actually see your 192.168 address, they only ever see your router's public face.
Finally, Section 5, securing your digital perimeter. Best practices you can actually use.
Theory is great, but putting it into practice is what actually keeps your data secure. Private IP networks relying on NAT don't just conserve IP space, they offer a massive security advantage. Because your private IP isn't globally routable, malicious external routers scanning the internet can't easily reach in and attack your laptop or smart devices directly. It inherently keeps your sensitive stuff isolated on the local network. And you really need that isolation, because let's face it, mistakes happen. Handling network bindings poorly can be an utter disaster. Just look at this Forbes headline. Hackers recently exploited an 18-year-old 0000-day loophole in major web browsers. Malicious external websites use this to bypass local security and mess with services running on users' local machines, all by routing requests through that 0000 wildcard. This is exactly why knowing the difference between a secure local host and an exposed wildcard is a huge deal.
All right, let's wrap up your toolkit with some concrete steps. 1. Regularly test your stack with the mirror test using ping. 2. Stick to 127.0.0.1 for all your local dev work to keep it fully isolated. 3. Run that open window audit with Netstat to ensure you haven't accidentally bound a private database to 0.0.0.0. And 4. Just verify your NAT is doing its job separating your private space from the public web.
So I'll leave you with this. If you opened your command prompt right this second and ran that netstat command, what open windows would you actually find? Run these diagnostics on your machine today and ask yourself, who really has the keys to your digital house? Stay curious, lock it down, and I'll catch you in the next explainer.